योगः कर्मसु कौशलम्.
Good day, dear participants. I, Dr. Hitesh Parekh, thank UGC Human Research Development Center of Gujarat University for giving me an opportunity to connect with you. I thank Dr. Jagdish Joshi, Professor and Director of UGC HRDC Gujarat University, and Course Coordinator Dr. Dilip Vasawa, Department of Chemistry, Gujarat University. The title of my today's talk is Chemistry, Supramolecular Chemistry, Fundamentals and Applications. Myself, Dr. Hitesh Parekh, and presently working as Associate Professor, Department of Chemistry, Sardar Patel University, Vallabh Vidyanagar. I did my Master and PhD from Department of Chemistry, Sardar Patel University, and title of my thesis is Studies on Novel Coordination Compounds involving biological important ligands. I was a postdoctoral fellow at University of KwaZulu-Natal, Durban, South Africa for 2.5 years. And my project title is Cavitan Cap Metalloporphyrin Catalyst for selective oxidation of linear paraffin. I worked as assistant professor at Department of Chemistry, Gujarat University from June 2015 to June 2022, and also worked as research scientist in various pharmaceutical industries. My research interest supramolecules and their applications, peptide chemistry, coordination chemistry, and homogeneous catalysis, and visited USA, Spain, and South Africa for research purpose. Published 34 full-length research article in UGC listed international journals, and recipients of UGC BSR Research Startup Grant of Rs 10 lakh. 3 PhD student and 2 MPhil student already awarded degree under my supervision, and 2 are currently working in the laboratory.
I gave invited talk and presented my research work at various seminar and conferences, and I am the active reviewer in the various international journals. Now we move to our today's topic, that is chemistry of supramolecules, fundamental and applications. So first of all, we need to understand what is supramolecules. So molecular chemistry, a term introduced by this gentleman, Jean Marie Lane, is chemistry beyond the molecules, that is the chemistry of molecular assemblies using non-covalent bonds. The 3 scientists in the picture, first one is C.J. Pedersen, the middle one is Donald J. Cram, and third one is John Marie Lane. They received Nobel Prize in 1987 for supramolecular chemistry. In 1967, Pedersen observed that crown ether showed molecular recognition, the first artificial molecule found to do so. Donald J. Cram established host-guest chemistry, where the host molecule can accommodate another guest molecule. In 1978, Lane proposed the term supramolecular chemistry. So together with Pedersen, Cram, and Lane, received the Nobel Prize for Chemistry in 1987. So supramolecular chemistry, a term introduced by Jane Mary Lane, is chemistry beyond the molecule. That means the chemistry of molecular assemblies using non-covalent bond. According to Dr. Lane, who invented the term, a supramolecule formed by association of two or more chemical species held together by intermolecular forces. Held together by intermolecular forces, that is hydrogen bonding, hydrophobic interactions, and coordination. Some historical notes on supramolecule means the development in the supramolecule. In 1891, a scientist Villiers synthesis cyclodextrin and used this compound for host gas studies. In 1893, Alfred Werner said that electronically saturated molecules can still bind if they have a mutual affinity to form complexes. In 1894, Emil Fischer developed lock and key principle for enzyme substrate interaction, which is related with selectivity and recognition. In 1906, Paul Ulrich said that molecules do not react if they do not bind. So any molecule, if they want to react, then it should be bind. In 1937, K.L. Wolff invented carboxylic acid gas phase dimer. And in 1939, Linus Pauling invented a new type of chemical bond, that is hydrogen bonding. In 1967, the three scientists, C.J. Pedersen, J.M. Lane, and Donald J. Cram, developed crown ether and cryptants, and they use this molecule for recognition and templating. And all these three scientists together in 1987 received Nobel Prize for supramolecular chemistry. They said that just as there is a field of molecular chemistry based on the covalent bond, there is a field of supramolecular chemistry, the chemistry of molecular assemblies and of the intermolecular bond. And recently in 2016, scientists Stoddard, Shivage, and Feringa received Nobel Prize for constructing molecular machines. So this is a new word for us, molecular machines. And this molecular machine could be used for new materials, sensors, and energy storage system. We can see here in the image, this is molecular chassis, and these four rotating molecular motors. So it's just like a molecular machine, just like a car. Supramolecular chemistry connected with various basic branches of the science, or we can specifically we can say various basic branches of the chemistry. So atom combines by covalent bond and form molecule, and this molecule may be inorganic, organic, and polymer. When this molecule interact with non-covalent interaction, it generates supramolecules and supramolecular assemblies. So this is a part of supramolecular chemistry. And when this supramolecular assembly and molecule or architecture used for certain application, used as a device, then it is a branch of material science. So atom by covalent bond form molecules. Molecules by non-covalent interaction form supramolecules and supramolecular assemblies, and they function as any device. Then it is it is included in the material science. So attraction and affinity, then selective binding, and then fixation and reaction. So molecular recognition is selective binding with a purpose. Molecular recognition is a selective binding with some specific reason, with some specific purpose. Self-assembly is a basic facet of the physical world. Electron, neutrons, and other subatomic particles assemble into atoms. These atoms assemble to give molecules. Molecules reacts with another molecule to resemble into new molecules, and molecules that may contain hundreds and thousands of molecules are called macromolecules. So starting from electron, neutron, and subatomic particles, they generate atom. Atom combines, gives molecule. Molecules reacts with another molecule, and we get a new molecule. And that molecule may contain hundred and thousands of molecules together. Then it is called macromolecules. Macromolecules are of two classes. That is polymer. We know that polymer, that means it has a repeating unit. And second, macrocyclic compounds and naturally occurring substance like steroids and alkaloids. In terms of macromolecules, all the polymers are macromolecules, but all macromolecules are not polymers, because for the polymer there is a condition: it must have repeated units. Macrocycles are described as the macrostructure having uncharged large ring leading to an intrinsic cavity. That means it should have a hollow space, and that space can be utilized by the any guest molecule. So these are the molecule which falls under this category: cyclodextrin, crown ether, cryptons, sepherins, rotexin, catenin, fullerenes, and calixarin fall under this category. When this macrocycle interact with other molecules by certain non-covalent interactions, such as dipole-dipole, ion dipole, hydrogen bonding, they are termed as supramolecules. Again, I repeat this. When macrocycle interact with some other molecules by certain, remember this word, non-covalent interactions, such as dipole-dipole, ion dipole, hydrogen bonding, they are termed as supramolecules. Supramolecular chemistry in nature, because we know this word DNA, naturally occurring DNA, this is a DNA helix, perhaps the best known self-assembling structure in the biological systems, exists in a double helical form. See, this is a single helix, this is another single helix, they combine together by this type of hydrogen bonding. The two single strands are held together by number of hydrogen bonds involving acidic hydrogen atoms, oxygen and nitrogen atoms. We can see in the side image. Let's see, this is a bond between oxygen and hydrogen, bond between nitrogen and hydrogen. So here hydrogen is donor, nitrogen is acceptor. Hydrogen is donor, oxygen is acceptor. So this is a hydrogen bonding and it is a self-assembling structure. Now, as per the definition of supramolecules, that is, it is a chemistry of non-covalent interactions. So here I explain about different supramolecular interactions, different supramolecular interactions. Non-covalent interactions represent the energy that hold supramolecular species together. So it give a energy, and because of that energy, the small molecules combine together and generate a supramolecular architecture. Non-covalent interactions are conceivably very weak than covalent interaction, which can range between 150 kilojoule per mole to 450 kilojoule per mole for single bond. This is about the covalent bond. Its energy strength ranges between 150 to 450 kilojoule per mole. Non-covalent bonds range from 2 kilojoule per mole for dispersion interaction to 300 kilojoule per mole for ion-ion interactions. However, when these interactions are used in a cooperative manner, a stable supramolecular complex can exist. So see, we said here this non-covalent interaction is have very low strength, but because of this synergetic effect of all this non-covalent interaction, we get a stable supramolecular compounds. The term non-covalent includes a wide range of attraction and repulsions, which are summarized in table 1.1. So these are the list of non-covalent interactions, or we can say supramolecular interaction. So the first in the list is ion-ion interaction. Its strength ranges between 200 to 300 kilojoule per mole. Second is ion dipole interaction. its strength ranges between 50 to 200 kilojoule per mole. Next is dipole-dipole interaction, that is 5 to 50 kilojoule per mole. Next is hydrogen bonding, 4 to 120 kilojoule per mole. Cation pi interaction, its strength ranges between 5 to 80 kilojoule per mole. Pi-pi interaction, 0 to 50 kilojoule per mole. Van der Waals forces, or we can say Van der Waals interaction, that is less than 5 kilojoule per mole, and hydrophobic interaction. So now let's see all this interaction one by one in detail. So first is ion-ion interactions. Ion-ion interaction which are very strong and the strength is in between 200 to 300 kilojoule per mole. These interactions are non-directional in nature. That means the interaction can occur in any orientation. Specific orientation or specific arrangement of the molecule is not necessary for ion-ion interactions. Here two example is given. The left hand side one is tetrabutyl ammonium chloride. It is a phase transfer catalyst where this ammonium ion interact with chloride ion. And the right hand side is acid base pair in particulars in protein. So this is oxygen, this is hydrogen, negative charge, positive charge. So it is interact with each other, ion-ion interaction. The next in the list is ion dipole interaction. They are moderately strong and strength in between 50 to 200 kilojoule per mole, but they are stronger when they are partially covalent. When it is partially covalent, then strength ranges between 100 to 400 kilojoule per mole. So it's nearer about the covalent bonding. Example is sodium complex of 15 crown 5. It acts as a cation binding host. We can see here this sodium plus ion interact with this 1, 2, 3, 4, 5 oxygen molecule. So it is a ion dipole interaction. The next example is terpyridine complex with ruthenium, where this nitrogen of this terpyridine ring attached with the ruthenium, bonded with the ruthenium, but these compounds are partially covalent. The next is dipole-dipole interaction. They are relatively weak and the strength is in between 50 to 200 kilojoule per mole. Despite being the weakest directional interaction, these dipole-dipole interactions are useful for bringing species into alignment, as the interaction requires a specific orientation of both the entities. We can see in the image dipole-dipole interaction in the acetone. So we can see in this image. For this dipole-dipole interaction, it requires specific orientation. That means it require a specific arrangement in the space. Then and then we can get this dipole-dipole interaction. Then another figure also shows there is a specific arrangement of this acetone molecule, and the dipole moment of this acetone molecule is 2.91 dBi. dBi is the unit for the dipole moment. Electrostatic interactions are caused by attraction between opposite charge, or we can say differently charged ions or dipoles. Ion dipole and dipole-dipole interactions, however, have orientation dependent aspects re- requiring two entities to be aligned such that the orientation are in optimal direction. Ion-ion interactions are non-directional in nature, meaning that the interaction can occur in any orientation. Electrostatic interaction play an important role in understanding the factors that influence high binding abilities, particularly in the biological systems in which there are a large number of recognition processes that involves charge-charge interactions. Indeed, these are often the first interaction between a substrate and an enzyme. The next is hydrogen bonding. So for hydrogen bonding, there are two necessary things required. One is hydrogen donor and one is hydrogen acceptor. So hydrogen bond donors are groups with hydrogen atom attached to an electronegative atom such as nitrogen or oxygen. Therefore, forming a dipole with the hydrogen atom carrying a small positive charge. While hydrogen bond acceptors are dipoles with electron withdrawing atoms by which the positive charge hydrogen atom can interact. For example, carbonyl moiety. We can see here in the image, this is a carbonyl moiety and this is a secondary amine compound. A carbonyl accepting hydrogen, this oxygen accepting this hydrogen from the secondary amine. So in general, the nitrogen in the secondary amine act as a donor and oxygen in the carbonyl act as a acceptors. The strength of hydrogen bonds can be very different between various systems and is not necessarily correlated with the Bronsted acidity of the proton donor. It depends on the type of electronegative atom to which the hydrogen atom is attached and the geometry that the hydrogen bond adopts in the structure. Typically, the strength range from 4 to 120 kilojoule per mole, with the vast majority being under 60 kilojoule per mole, and scales of hydrogen bond acidity and basicity have been developed. These are the various type of hydrogen bonding geometries. That is, the first one is linear, second one is B is bent, third is donating bifurcated, this one is fourth one is accepting bifurcated, the fifth one is trifurcated accepting, and the sixth one is three center bifurcated. So these are the various type of hydrogen bonding geometries. Hydrogen bonding type 3, the most important non-covalent interactions in the design of supramolecular architectures. Because of its strength and high degree of directionality, it represents a specific kind of dipole-dipole interaction between a proton donor and a proton acceptor. It represents a special kind of dipole-dipole interaction between donor and acceptor. The high directional nature of hydrogen bonding interaction together with specific alignment of hydrogen bond donors and acceptors have proved to be a fruitful asset for the design of supramolecular system. So in the table 1.2, the hydrogen bond interaction and their properties are given. Donor hydrogen to acceptor. So this type of hydrogen bond, mostly it is electrostatic or sometimes it is like a covalent bond. The bond energy ranges between 12 to 120 kilojoule per mole, 12 to 120 kilojoule per mole, and bond length between hydrogen to acceptor, that is ranges between 1.2 to 3.2 angstrom, and donor to acceptor, it ranges between 2.2 to 4.0 angstrom, and bond angle ranges between 90 to 180 degree. Now the next interaction, which is very very important, which is pi interaction. There are two main pi interactions are found in supramolecular system, namely cation pi interactions and pi interaction. So first, this cation pi interaction are well known in the field of organometallic chemistry, whereby olefinic groups are bound to transition metal center, for example, ferrocene and zinc salt, but these are not regarded as non-covalent interaction. So cation pi interaction are well known in the field of organometallic compounds. We can see in the figure zinc salt, where this alkene CH2 double bond CH2 is bound to this platinum transition metal like this. And in the ferrocene, two cyclopentadienyl ring, the top one and bottom one, it is also called, we know this, it is also called sandwich type of compound. So they bound with the iron metal atom, and hapticity of this compound is 2 and hapticity of this compound is 6. Cation pi interaction, they are relatively weak and the strength ranges between 5 to 80 kilojoule per mole. Alkaline and alkaline earth metals also form interaction with double bond system. For example, the interaction of potassium ion with benzene has a similar energy to the K plus OH2 interaction. So we can see here figure the interaction, cation pi interaction is 80 kilojoule per mole in gas phase system, where this benzene molecule have pi electron density. It attracts this positively charged K plus ion. The next is pi interaction. They are relatively weak and strength ranges between 5 to 50 kilojoule per mole. The two types of pi interaction are there. First, phase to phase. This is shown here in the figure A, and H2 phase, which is shown in the figure B. Phase to phase and H2 phase. And in the side figure, top and side view of layer structure of graphite. We know this, the graphite has layer structure. So layer structure of graphites held together by phase to phase interactions. The layer structure of graphite is held together by weak face-to-face interaction and therefore feels slippery. Therefore, it feels slippery, and it is because of this slippage between layers that graphite can be used as lubricant as as it is used for the writing purpose as pencils because this layer slip on each other. Interactions involving pi system can be found in nature. For example, the weak face-to-face interaction between base pair along the length of double helix are responsible for the shape of DNA, which we already discussed in supramolecular chemistry in nature. The next is van der Waal interaction. We can say van der Waal forces, which is also called mutually induced dipoles. Van der Waals interaction are dispersion effects that comprise two components. Namely, the first one is London interaction and the second one is exchange and repulsion interaction. They are very weak and strength ranges between 2 to 20 kilojoule per mole. Van der Waal interaction arise from fluctuations of the electron distribution between species that are in close proximity to one another. In the image, we can see here London interaction between two argon atom. The shift of electron cloud around the nucleus produce interstitious dipoles that attract each other. We can see the electron cloud move towards this side. So this nucleus is positively charged and this electron cloud is negatively charged. So they interact with another molecule. And the last one in the non-covalent interaction list is hydrophobic effects. Hydrophobic effects arise from the exclusion of non-polar groups or molecules from aqueous solution. This situation is more energetically favorable because water molecules interact with themselves or with other polar group or molecule preferentially. Two organic molecule creating a hole within an aqueous phase, giving rise to the entropy hydrophobic effects. One hole is more stable than two. So this organic molecule moves this side and gives this hole, and then they interact with each other. Now, very important term in the supramolecular chemistry, that is host-guest chemistry. So molecular chemistry, it is related with the covalent bond. And when this molecule combined with non-covalent bond, combined with the various interactions which we already discussed, they are called supramolecular chemistry. So this is a one molecule, this is another molecule. By covalent synthesis form a host, we can say receptor, or we can also call them molecular building blocks. And when this host molecule accommodate this guest inside it like this by non-covalent interaction, it is called supramolecule. Now I am going to discuss about various supramolecular platforms. Generation of supramolecules. Supramolecular chemistry, which is defined as chemistry of non-covalent interaction or as the chemistry of molecular assemblies can be classified by their generation on the time scale. So on the generation on the time scale means by their time of invention. So the first generation is cyclodextrin. It is abbreviated as CDs. Second one is crown ether, and the third one is calixarins. Now, the first generation of supramolecule, that is cyclodextrin. Cyclodextrin are synthetic substance obtained from the enzymatic degradation of one of the most essential polysaccharides, that is starch. So cyclodextrin can be synthesized from the starch. Cyclodextrin were originally observed by Villiers in 1891 using Bacillus amylobacteria as enzymes. Here we can see on the slide, it is an image of beta cyclodextrin. The figure A on the left hand side, which is molecular model of beta cyclodextrin, and in the right hand side it is a chemical structure of beta cyclodextrin. The cyclodextrin containing 6 D-glucopyranoside units. So this is a glucopyranoside unit. When the cyclodextrin contain this type of 6 D-glucopyranoside units, it is called alpha cyclodextrin. It contains 7 glucopyranoside units. It is called beta cyclodextrin, and it contains 8 D-glucopyranoside units. Then it is called gamma cyclodextrin. And all these are this D-glucopyranoside units linked by 1,4 glycosidic bonds. The family of cyclodextrin include 5 members to 12 member units. So we can get a 5-member cyclodextrin, and maximum we can get a 12 D-glucopyranoside unit in a cyclodextrin. On an industrial scale, beta cyclodextrin are produced using enzymes cyclodextrin glucanotransferase. The name of the enzyme is cyclodextrin glucanotransferase. The industrial importance of cyclodextrin was identified in 1948 when the crystal structure of gamma cyclodextrin was solved by Fredenberg and Kramer. So it is synthesized in 1891, but their importance was identified, developed in 1948 after the identification of the compound and their structure. The structure revealed the cyclic nature of the compounds and their potential to include guest molecule. So cyclodextrin have a hollow cavity, and that cavity can accommodate any guest molecule. The narrow lower rim, which bristles with 2 primary hydroxyl group per dextrin repeating units. So the lower narrow rim has 2 hydroxyl group, and that look like a bristle on this dextrin unit. Properties of cyclodextrin: their outward pointing hydroxyl groups make the cyclodextrin water soluble while retaining a hydrophobic central cavity. The aqueous solubility of beta cyclodextrin at room temperature is very low, that is 18 gram per liter. Then the alpha and gamma cyclodextrin. Alpha cyclodextrin has solubility 145 gram per liter, and gamma cyclodextrin has solubility 230 gram per liter respectively. All the cyclodextrin are 7.9 angstrom in depth. However, the outer diameter and cavity size increases with the number of cyclodextrin unit. That means with the number of repeating D-glucopyranoside units. This gives alpha cyclodextrin an overall diameter of 14.6 angstrom and a cavity size around 5 angstrom. Beta cyclodextrin 15.4 angstrom and the cavity size is 6.5 angstrom, and gamma cyclodextrin diameter is 17.5 angstrom and the cavity size is 8 angstrom. We can see in this image that is this D-glucopyranoside units. It is bonded via 1,4 glycosidic bonds. The first figure is alpha cyclodextrin, which has a 6 repeating units. It has a cavity diameter in between 4.7 to 5.3 angstrom. Beta cyclodextrin, which has a 7 repeating units and the cavity diameter is 6 to 6.5 angstrom. And gamma cyclodextrin, which has a 8 D-glucopyranoside units and which has a cavity diameter of 7.5 to 8.3 angstrom. And the height of this torus is 7.9 angstrom for all this alpha, beta, and gamma cyclodextrin. The hydroxyl group on the upper and lower rim of cyclodextrin are good site for substitution. However, due to the chiral nature of parent compounds and large number of repeating units, the derivatization of cyclodextrin is a complicated matter. The crystal structure shows that cyclodextrin in complexes adopts down structure with all glucopyranoside units in the 4C1 chair conformation. So all these D-glucopyranoside units in chair conformation. Apart from this naturally occurring cyclodextrin, many cyclodextrin derivatives synthesized in the laboratory. These derivatives are produced by amination, esterification, etherification of primary and secondary hydroxyl group of the cyclodextrin. Depending on the substituents, the solubility of cyclodextrin derivatives is different from that of parent cyclodextrin. Virtually all derivatives have a change hydrophobic cavity volume, and also their modifications can improve solubility and stability against light or oxygen and help to control the chemical activity of guest molecules. The synthesis of uniform cyclodextrin derivatives requires regioselective reagents, optimization of reaction condition, and a good separation procedure. So if anyone wants to synthesize this cyclodextrin in the laboratory, we require these three main things: regioselective reagents, optimization of reaction condition, because this repeating unit, whether it is cyclized into 6, 7, 8 or greater than 8, we don't know. So we require specific optimized reaction condition, and it also gives different isomers at the same time. So we require good separation procedure. The most frequently studied reaction is an electrophilic attack at the hydroxyl group, the formation of ethers and esters by alkyl halides, epoxides, acyl derivatives, isocyanates, and by inorganic acid derivatives such as sulfonic acid chlorides. Cleavage of carbon and hydroxyl bonds have also been studied frequently, involving a nucleophilic attack by compounds like azides, halides, thiols, thiourea, and amines. This require activation of oxygen atom by an electron withdrawing group. Because of their ability to link covalently or non-covalently, especially to the other cyclodextrin, cyclodextrin can be used as building blocks for the construction of supramolecular complexes. How we can modify the cyclodextrin and what we can get from the cyclodextrin, we can see here modification. If we do grafting of this cyclodextrin, we get amphiphilic cyclodextrin. Self-assembly gives self-assembled structure. Order assembly or cross-linking gives cyclodextrin molecular imprints. Polymerization of cyclodextrin gives nanosponge, and covalent conjunction with cross-linking gives cyclodextrin complexes, nanoreservoir, and multilaminar vesicles. Biological activities of cyclodextrin. Cyclodextrin appears to be extremely compatible. They are unable to significantly permeate biological membranes and are not absorbed by the gastrointestinal tract, yet do not include a response from the body immune system. Tests on rats indicate that LD50 values for the most toxic parent compound, that is beta cyclodextrin, are greater than 5 gram per kg of body weight when administered orally and zero point 0.5 gram per kg of body weight when administered as intravenous injection. This low level of toxicity coupled to the cyclodextrin ability to form inclusion complexes make them ideal excipients in pharmaceutical formulations. These are the properties listed for alpha cyclodextrin and beta cyclodextrin. Number of D-glucopyranoside repeating units, 6 in alpha and 7 in beta cyclodextrin. Molecular weight 972 gram per mole and 1135 gram per mole for alpha and beta cyclodextrin respectively. Solubility in water at 25 degree, 14.5 gram per liter for alpha cyclodextrin and 1.85 gram per liter for beta cyclodextrin. Outer diameter 14.6 angstrom for alpha and 15.4 angstrom for beta. Cavity diameter 4.7 to 5.3 for alpha cyclodextrin and 6.5 to 6.6 to 6.5 angstrom for beta cyclodextrin. Height of torus is same for alpha and beta, that is 7.9 angstrom, and cavity volume 174 for alpha cyclodextrin and 262 for beta cyclodextrin. Applications of cyclodextrin. Cyclodextrin have wide range of applications. It is used in cosmetics and toiletries. It is also used as in catalysis, in biotechnology. It is used in textile and paper industry. It is used in formulation of detergents, glues, and adhesives. It is also used in polymer industry. It is used in pharmacy and medicine. Cyclodextrin also used in food industries, and the main importance of cyclodextrin, application of cyclodextrin, it can form inclusion complexes. Here we have a list that contain drug cyclodextrin inclusion complex. So these are the list of drugs. For the inclusion complex, alpha cyclodextrin, beta cyclodextrin, 2-hydroxy-propyl beta cyclodextrin, randomly methylated beta cyclodextrin, sulfobutyl ether beta cyclodextrin, and 2-hydroxy-propyl gamma cyclodextrin use with these various drugs, and they form a inclusion complex. The second and very important generation of supramolecules, that is crown ether. Histology of crown ether: C.J. Pedersen 1967 synthesized crown ethers and awarded Nobel Prize in chemistry without having PhD degree. So C.J. Pedersen is known as father of crown ether. Crown ether is a generic name given to macrocyclic polyether. We can see in the image macrocyclic polyether containing ethylene bridges. This is ethylene bridges, CH2 dash CH2, separating electronegative oxygen atom. The discovery of macrocyclic polyether is interesting in recent developments of separation chemistry. They typically contains central electron rich hydrophobic cavity with diameter varying from 1.2 to 6.0 angstrom. So in the image, the scientist who invented crown ether is C.J. Pedersen, and the second image is 18 crown 6. 18 means the total number of atom in the ring, and 6 number, it is a number of heteroatom, and it is separated by ethylene bridge CH2 CH2. The discovery of crown ether leads an enormous advance in chemistry. The hydrophobic cavity is ringed with electronegative binding heteroatoms such as oxygen, nitrogen, sulfur, which in turns are surrounded by a collar of CH2 groups, forming a framework which is flexible and exhibits hydrophobic behavior. The hydrophobic exterior allow them to solubilize ionic substances into non-aqueous solutions and in membrane media. Discovery of first crown ether. The scientist C.J. Pedersen was working as an industrial chemist in DuPont industry, and a project was initiated in 1961 by him. What is the project? The hypothesis is to find out a new vanadium containing catalyst for the polymerization of olefins. Pedersen decided to study the effects of uni and multidentate phenolic ligands on the catalytic properties of vanadial groups. Quinky means penta. Quinky dentate ligand selected was base 2 orthohydroxy phenoxy ethyl ether, and the synthesis was begun according to the route outlined in scheme 1. So this is resource catechol, and starting from this route, they get the final product. This is quinky dentate ligand base 2 orthohydroxy phenoxy ethyl ether. But during the synthesis of ligand from catechol, a small quantity of byproduct in the form of silky crystals was obtained, which shows strange solubility behavior, which led to further spectroscopic studies and resulted in the discovery of the first crown ether, which is named as dibenzo 18 crown 6. Since then, large number of crown ethers was synthesized. So here we can see in the scheme A, catechol by this reaction, the final product is quinky dentate ligand. This is bis 2 orthohydroxy phenoxy ethyl ether. And this is the byproduct, and which is dibenzo 18 crown 6, which has a strange solubility behavior. These are the other derivatives of crown ether: 12 crown 4, 15 crown 5, 18 crown 6. Diaza 18 crown 6 means in this 6 heteroatom, 2 are this nitrogen, diaza 18 crown 6, and the first compound is dibenzo 18 crown 6, which is synthesized first in the laboratory. Classification of crown ethers. The organic neutral ligands are classified into 3 groups, that is podents, coronants, and cryptants. So podents, these are the open chain compound and are characterized by linking ring and bridge structure. So this is a structure of podent. We can see here it does not have a closed ring structure. It is a open chain structure. So it is called podent. Coronants. Coronants means it is a crown ether. They are cyclic compound. Coronant containing oxygen as donor atom are called crown ether. Those containing oxygen and nitrogen donor atom are called as a crown ether, and those containing oxygen and sulfur are called thia crown ethers. And the third one is cryptants. They are macro polycyclic polyethers. Macro polycyclic polyether are classified into bicyclic, tricyclic, and tetracyclic compounds. Applications of crown ethers. Crown ether are used in membrane transport. It is used as chromoionophore or fluoroionophore. It is used in extractive separation analysis. It is used as phase transfer catalyst. It is used in ion chromatography. Crown ethers are used in isotope separations, used as ion selective electrodes, and molecular recognition. The third generation of supramolecule, that is calixarine. The term calixarine was given by C.D. Gutse in 1978. Calixarine is derived from Greek word that means calyx. Calyx means vase or cone-shaped molecule. We can see here in the bottom image, it is look like a cone or vase-shaped molecule, flower pot. Two different zones can be distinguished, the lower rim and the upper rim. The lower rim is phenolic hydroxyl group, and the upper rim is para position of phenol tertiary butyl group. In the left hand side image, the main compound para tertiary butyl calixarine. In between, this is calixarine, and this the middle image is showing upper rim and lower rim. Lower rim has 4 hydroxyl group, and upper rim has the para position of the phenol, and it is a cup, vase or cone shaped structure. And the resorcine for arene, it is also in the category of calixarine. In these slides, we can see the calyx 4M arene, calyx 6 arene, and calyx 8 arene, the derivatives of various calixarine, and the scientist C.D. Gutse and his wife Alice Gutse with the molecular model of calixarine, and it is shown here. It is like a fast structure. Calixarin may be divided into two broad classes, that is heterocalixarin and heterocalixarin. Heterocalixarin means when a organic moiety, pyrrole, furan, pyridine, they are called as heterocalixarin. That is, this is a calyx pyrrole, calyx thiophene, and calyx furan. So when this type of heterocyclic moiety used in this structure, it is called heterocalixarin. Examples are calyx pyrrole, calyx thiophene, and calyx furan. Heterocalixarin, when the methylene junction involves element like sulfur and oxygen, they are called heterocalixarin. Example is thiacalixarin and oxacalixarin. And in comparison with the earlier structure, see, we have a CH2 bridging group everywhere. But here, instead of CH2 bridging group, we have a sulfur. So it is called thiacalixarin. And in this figure, we have a oxygen. So it is called oxacalixarin. Calixarin conformers. The rotation of the phenolic moiety about the bridging CH2 group. This bridging CH2 group is possible in calyx 4-arene. So this calyx 4-arene observed four principal conformers. They are cone. This is partial cone. So one phenolic moiety is inverted, 1-2 alternate, and 1-3 alternate structure. The four conformers of calixarin are cone, partial cone, 1-2 alternate, and 1-3 alternate. Hayes and Hunter's stepwise synthesis of calyx 4-arene. Hayes and Hunter's synthesis start using paracresol as starting material, and the final product is para-methyl calyx 4-arene. The final product is para-methyl calyx 4-arene. The synthesis provide a classic example of the use of a blocking group that is added at one point to protect a reacting site, and then removal at the lower stage data points to reopen that site for the reaction. So here in the first step, the paracresol is converted to 2-bromo-4-methyl phenol by this protecting group, by this bromine. They protect the reacting site by this bromine, and later part, this bromine is removed by hydrogenation and again get this reactive site, and then this molecule cyclize and we get our final product, that is para-methyl calyx 4-arene. Synthesis of various calixarin derivatives. Synthesis of this calixarin derivatives was reported in acidic as well as basic condition. This is a synthesis of calyx 4-naphthalene. Orthonaphthol yields a mixture containing 60% of calyx 4-naphthalene, this one, along with two other isomers, that is 9.6% and 5%. So what are the isomer? We can see here the orientation of this hydroxyl group, it differ, then we can get a different isomer. The next is tetramethoxyresorcin 4-arene. This is a chiral molecule. Preparation of enantiomerically pure tetramethoxyresorcin 4-arene was reported by our research group. 3-methoxyphenol, it condenses with this aldehyde in presence of acidic condition, BF3 ethate. Then we get a racemic mixture of tetramethoxyresorcin 4-arene. This racemic mixture is separated by using this compound. that is S, S minus 1 phenyl ethyl isocyanates and dibutyl teen dilaurate as catalyst, and we can get the two different isomer of this tetramethoxy resorcine for arene. The next synthesis is 2,6-dihydroxyacetophenone, 4 arenes. It is developed by our research group. So the electron withdrawing group at this second position, this is second position. Electron withdrawing group at the second position of resorcinol is very difficult to cyclize, but in the presence of sodium methoxide as base, in the presence of sodium methoxide as base, it cyclized and yielded 2,6-dihydroxyacetophenone for arene. And this compound used for the amino acid recognition. Metacyclophanes containing heteroatoms such as oxygen, nitrogen, and sulfur, rather than methylene groups as bridging moiety, also qualified a member of calixarine family. So oxacalixarine, azacalixarine, and thiacalixarine, they are also in the calixarine family. So the first synthesis of oxacalixarine was given by Schomer and Stepp, that is resorcinol plus 1,5-dichloro-2,4-dinitrobenzene, and we get a oxacalixarine. In similar way, we can also get a thiacalixarine. Resorcine for arene cap metalloporphyrin. This work I've performed during my postdoctoral study at University of KwaZulu-Natal, Durban, South Africa. The final product is resorcine for arene cap metalloporphyrin, and we synthesize resorcine for arene porphyrin nickel 2. This is in the center, there is a nickel metal. The crystal structure, compound synthesized, purified, and developed a crystal structure. The synthesis start with the resorcinol that is converted into octol. Octol, then bromination at the second position gives bromooctol. Then the ball closing reaction. This upper side is closed, so it is a fixed, not flexible ring. It is a fixed ring. Bromoball. Bromoball is converted to hydroxyl ball, and this hydroxyl compound reacts with bromo alkyloxybenzaldehyde, gives tetraaldehyde ball, and this tetraaldehyde ball in presence of pyrrole and propionic acid gives this resorcine for arene cap porphyrin, and via metallation in the microwave condition we get the resorcine for arene cap porphyrin nickel 2, and this compound is a look like a structure of cytochrome P450, and which is used for the oxidation of which is used as a catalyst for the oxidation of linear paraffins. Some other structure in the calixarine family, this is cyclotriveratrilene CTV. So 3-member 1, 2, 3, 3 aromatic ring veratrol, which is converted to cyclotriveratrilene, and this is the crystal structure developed by our research group. We can see it has a hollow space or cavity in between the structure. The next compound is pyrogalerine, that is prepared from pyrogalol, and another structure is pillar 5-arene, which is also developed by our research group. So pillar 5-arene means which has a ethoxy group as para position and the CH2 bridge at also para position, and 5 aromatic ring were there. So it is a side view of the compound. This is a top view of the compound, and this crystal structure developed by our research group, and we can see in the cavity of this pillar 5-arene there are two CH2Cl2 dichloromethane moiety is trapped during the crystallization process. in the cavity of this molecule. Now, how we can functionalize this different calixarine derivatives? So calixarine can functionalize on this hydroxyl group or on this upper rim carbon. Similar way, the functionalization of resorcine for arine performed at this hydroxyl group. You can add any choice of group here. You can change this aldehyde and get different R here, and we can add any new active compounds at active functional group at this upper rim carbon. Functionalization of calyx pyrrole, that is at the R alkyl chain of this structure and the periphery of this pyrrole moiety. Periphery carbon of the periphery of this pyrrole moiety can be substituted by another groups. Derivatization of thiacalixarine can be done at sulfur atom, at upper rim carbon and the hydroxyl group, and the derivatization of oxacalixarine can be done at upper rim carbon and hydroxyl group. Applications of calixarine and application of calixarine families members. So it is used as fluorescent recognition. It is used in drug delivery system. It is used as fluorescent material. It is used as artificial enzymes. And this synthesized calixarine compound, that is resorcine 4-arine derivatives, which is used as liquid crystal material, used in catalysis. It is used in sensing applications of anion, cation, organic molecules, amino acid, pesticides, fungicides, and some explosives. Analytical technique for molecular separation. It is used in drug delivery and fluorescent chemosensor. So, importance of supramolecules. Due to great varieties of ways for their further functionalization. So we can functionalize this supramolecule by number of ways, and we can get a different number of derivatives. Versatile complexing property. It can form a complex with anion, cation, any guest molecule. It can have an interaction with amino acids. So it is used as sample sensor. So it is a versatile complexing properties. It also has conformational flexibility. We can see the structure has hollow cavity and number of hydroxyl group are there, and they have a different conformation. Easy synthesis. The synthesis step is very easy and simple, and all the key starting material and reagents are commercially available and at a low cost, economically cost. And eco-friendly synthesis means the synthesis of this supramolecule has very less pollutant reagents. And all these supramolecules, they have found to function as, these are the function application in general. So this supramolecule use as macrocyclic receptors, dendrimers in biological systems, nanocapsules, nanoparticles as nanosponge, optical chemosensors, supramolecular tectons and host molecules, components in liquid crystals. It is function as photoresist material in selective membranes, surface reforming agents. It is used as HPLC stationary phase. It is also used as ligands for MOPs, means metal organic frameworks. It is key starting material for molecular machines as ion channel mimics and metal ion extraction agents. So these are the number of uses of these supramolecular compounds. So as per your expertise and convenience, functionalize them with those functional groups with which you are comfortable with, or you are already working with and allow them to function as per your desired function. So whatever active compounds are available with you in your laboratory, that compound attach on this supramolecular architecture, and we can get a different types of function. So I am sure that they will function better than your expectation. So you will get मिलेगा उम्मीद से ज्यादा. So you will get a better function. I assure that you will get a better function than your expectation. Why we get a better function than our expectation? These are the reasons. More number of functional groups. If suppose take an example of resorcine for arene, we have a 8 hydroxyl group on a upper rim, 4 carbon on upper rim of aromatic carbon, and we have a 4 bridging groups. So we can substitute this 16 places. So it has a more number of functional groups. Functional group may be circularly arranged or pre-organized. May acquire different conformation, that is cone or partial cone. So depending on the nature, it is like cone or sometimes it's a partial cone structure. Enhance, reduce binding, enhance or reduce binding due to hydrogen bonding. Hydrophobic nature of macrocycles may influence the binding due to intrinsic cavity or hollow space, and possibility of hydrogen bonding in these supramolecules may allow this compound to behave as ditopic and tritopic receptors, and after functionalization they may form superstructure by self-assembling. So special notes for this talk. Coffee never knew it would taste so nice and sweet before it met milk and sugar. So we are good as individual, but become better when we meet and blend with right people. So the take home message is collaborate with your friends, colleague, or nearby institute. So suppose a person have idea and another person has idea, both collaborate, then the idea become a best idea, and it also overcome the lacking of the person. And I saw one, this is a one reference there. This physics paper has a record, it has a 5154 author. So that much large collaboration in this paper. I would like to acknowledge my research scholar, my research group, and the coordinator of the course, Dr. Dilip Vasava, and Professor Joshi, Director, UGC HRDC, Gujarat University, and especially Gujarat University for giving me this opportunity. Thank you. And my contact number is 98980 74059. We are ready to collaborate with any institute for research purpose. Thank you. Thank you so much.
Thank you very much, sir. It was very nice and informative session for all. Thank you very much once again.